Sure, thanks so much. It was pleasure working with Presley on the understanding formation of Venus, specifically in our solar system. The project was to determine how much giant planets, specifically Jupiter and Saturn, affect formation of terrestrial planets, in particular the similarity between Venus and Earth. And Presley did a fantastic job analyzing the results and actually extracting the underlying secrets that demonstrate how Jupiter will play an important role. I'm sure you will enjoy her presentation. Thank you.
Right. And Presley, would you like to share your screen or should I?
Could you share your screen, please?
Yes.
Thank you so much. So, as aforementioned, I'm Presley, and today I'm going to be talking about the research that I did with Dr. Haghighipour about the effects of the giant planets on the formation of Venus. Could you go to the next slide, please? So, Venus and Earth are very, very similar. We can see that on the slide, the mass is 82% of Earth's mass, and the radius is 95% of Earth's radius. So Venus is basically the same size and shape as Earth, which is very interesting. And we wanted to research why this is. And could this be because of the gravitational perturbation of the giant planets, such as Jupiter and Saturn? Go ahead and go to the next slide. So in order to answer that question, Dr. Haghighipour simulated the formation of the terrestrial planets, and I analyzed the results. Here is a little bit of the detail on the simulation. So the N-body integrator that was used creates a few hundred moon to Mars-sized bodies, which are known as embryos, and then a few thousand small kilometer-sized objects known as planetesimals. We integrate their orbits using an N-body integrator called Mercury. And then when they physically collide, the bodies merge perfectly. There is a conservation of momentum in inelastic collisions. And the graphic that we have here shows that the mass becomes one integrations until final bodies reach stable orbits around 200 million years of integration. And then we integrated the system for different configurations
Presley frozen for anybody else?
Oh no, that's no good.
You're back now.
Okay, well, where did you drop off?
You're describing the figure.
Okay, so the figure shows that the mass is conserved as well as the momentum. They merge into one final larger body. We continued the integrations for about 200 million years until these objects reach stable orbits. And then we integrated the system for different configurations of Jupiter and Saturn so that we could see the effects that Jupiter and Saturn had by changing their eccentricity. Go ahead and go to the next slide. So here is a graph of Jupiter and Saturn with their current orbital elements, which means the way that things are now and the way that we know them. Each panel with the time showing in the upper right corner. So you can see it goes from 0 to 200 million years. That is what MYR stands for. At each panel, the sun is at the origin. It's not shown because it's very large and would make these graphs impossible to read. And Jupiter and Saturn are in their orbits, which fall outside the picture since the picture only goes from 0 to 5. And Jupiter falls at 5.2 and Saturn at 10 AU. So the panel at the very start shows all of the planetary embryos, which are in colors, and the planetesimals are in gray in the background. The color coding shows the amount of water in each object. It is not relevant to this project, but it is an interesting thing to keep in mind if you want to pay attention to it while looking at the other graphs, if that's something that's interesting to you. Note that in our current simulation, it takes about 200 million years for the planets to form and be in stable orbits. These simulations are not exact. This is not entirely exactly how our solar system formed. We can't go back in time and look. It doesn't produce the exact solar system. We instead use them to determine the underlying physics and prove a concept. This is not perfect. There are too many variables to account for in an exact computer simulation. However, we have the next slide. This is Jupiter and Saturn in their current orbit with an eccentricity of 0.1. They both have relatively low eccentricities, and so we cranked it all the way up to 0.1, which essentially increases the interaction of the giant planets with the material interiors. So it is a very exaggerated version of the effect that it has. And as you can see, because of this gravitational influence, most of the material is ejected by the giant planets interacting with a disk, and only one planet ends up forming. Go ahead and go to the next slide. Here is Jupiter and Saturn completely removed, which is really interesting to me. There will be absolutely no influence from either planet at all. And as a result, a lot of planets have formed, as shown here. If the solar system did not have Jupiter and Saturn, there would be no uniform asteroid belt, and the inner solar system would have had many, many more planets. But because of Jupiter and Saturn, no planets can form in the asteroid belt region in our solar system, and the solar system maintains an asteroid belt instead of the asteroids and these planetesimals just being scattered throughout and many planets forming. So go ahead and go to the next one. This table right here summarizes the results as shown by the two columns showing the number of planets. As the eccentricities of the giant planets increase, the number of planets decreases, as well as when Saturn is removed, the number of planets increases. Could you try and click on the slide and see if something happens? It might not work. Yeah, that's fine. So you can also see on the table that when Saturn is removed and Jupiter has low eccentricity, the planet that is a Venus analog shows greater similarity to Earth. So this suggests that Jupiter plays the underlying role in Venus's mass and size being similar to that of Earth, and that Saturn actually sort of balances it out in a way. You can also see that I calculated the percentage of the mass in the disk that goes towards making planets versus the percentage that gets ejected. And you can see that a very, very small percentage of the mass inside the disk actually goes towards planetary formation, which is why these terrestrial planets are so small and exist in the state that they do today. Go ahead and go to the next slide. So the results of our study show that it is the effect of Jupiter that causes the mass and size of Venus to be similar to that of Earth. Saturn does not play a role in that specific thing. The results also demonstrate that terrestrial planets are small because of the perturbation of giant planets, causing a large amount of the disk to be ejected out of the system. Only a small amount actually goes into planetary formation. Without the giant planets, there would have been no asteroid belts, and planets would have formed where the asteroid belt currently is. And Jupiter and Saturn are the reason that our solar system does not have super Earth planets, which would have happened if a bunch of those planetesimals formed into big planets with being loose without the effects of Jupiter and Saturn keeping them in check. Go ahead and go to the next slide. I'd like to thank my mentor, Dr. Hagigipur, for guiding me through this amazing project and giving me the confidence and freedom to present my findings, the creators of the N3 program for providing amazing accommodation and support for my autism and providing opportunities in space science for people like me, my father for helping me with the calculus integration and being just as invested in this as I am, and most importantly, my co-author Domino for his scientific advice and support. You can see him on the slide there, my beautiful co-author. So yeah, thank you guys so much for having me and allowing me to present my findings. This has been an amazing experience.
Great, thanks, Presley. I love acknowledging our fuzzy, furry co-authors in our presentations. I should do that more often. Does anyone have any questions for Presley before I move on to our next presenter, which will be Asher?
Oh, I have a question. So were these results about how important Jupiter was? Was that known before by other modelers? And you used a different approach to come up with the same result, or is this like a totally new result?
More or less, I'm not an expert in the field. I can field that question over to my mentor to make sure. I think that there hasn't been like a ton of research specifically on affecting Venus. However, we are aware of how the planets interact with each other. This is just a bunch of data analysis to prove that point and consider why that could be.
Should I explain a little more?
Yes, please go ahead.
Yeah, sure. Yeah. No, these are brand new results. The effect of Jupiter and Saturn on terrestrial planet formation has been known, but it's been only recently that we learned why these planets and terrestrial planets form interior to 2.1 AU, why they have small masses, And more importantly, this is the first time that anyone has to actually look into the underlying physics of why Venus forms first and why it is similar to Earth. So the results are brand new. I'm planning to present them later this year at the Planet Formation Conference.
Well, that's even more exciting. Great job, Presley.
Thank you so much.